Hello and welcome back to Epperly Notes. Today we'll be covering Lesson 2, Section 2.1, Existence and Uniqueness Theorems, First Order Equations. So let's get started. A differential equation of the form y prime plus p of t y equals g of t is called the first order linear differential equation. The equation is called homogeneous if g of t equals 0. The equation is called non-homogeneous if g of t does not equal 0. So y prime plus t squared y minus 2t equals 0 is non-homogeneous because of that 2t term. If that 2t term was on the other side from the y prime plus t squared y, it would be homogeneous, as seen in y prime plus t squared y equals 2t. That is homogeneous. So, order is the largest derivative. That is a reminder from the previous lesson. Let's work an example now. Y double prime plus 2e squared plus 2y prime times y equals 9t. This would be a second order equation because of that y double prime. And this equation is considered nonlinear because of the 2y prime times y. The variables are multiplying into each other, which is what makes this nonlinear. The next example, it says t cubed d squared y over dt squared plus t dy over dt plus 2y equals e to the t. This is again a second order equation because of the d squared y over dt squared. So that would be equal to y double prime. And this was also considered linear because all of the derivatives and y are all by themselves. The t cubed, t, e to the t do not contribute to if we consider this equation linear or nonlinear. And for our next example, we have which of these equations are first order, which are linear, which are homogeneous. And we have the given equations, A, B, C, D. A states y prime equals xy cubed times x squared plus 1 to the 1/2, and we are given the interval y to 0 equals 1. Our next equation B, t squared y prime plus 4ty equals cosine of t, and we're given the interval y of -1 equals 2. Next equation C, y prime equals t to the square root of y, and we're given the interval y to the 0 equals 0. And finally, our last equation D, t squared minus 4t, all of that times y, plus ty equals e to the t, and the interval is y of 2 equals -1. If you notice, all of these equations are first order. There is nothing that goes past the first derivative in any of those equations. So, how about if it's linear or homogeneous? Well, in A, we consider that nonlinear because of the y cubed. And if we solve this equation for y, we would get y prime minus xy cubed times x squared plus 1 to the 1/2 equals 0, which if you remember, that means it's homogeneous. So if a problem can be solved with the variables on one side and get it equal to 0, that means it will be homogeneous. Now for equation B, this is considered linear because because of the y terms are by themselves, and it is also non-homogeneous because it is equal to something. And in B, it was equal to cosine of t. Now for equation C. C is considered not linear because of the square root of y, and this one is also considered homogeneous for the same reason that A was considered homogeneous. And for our final equation D, it is also linear and it is non-homogeneous because it is equal to something, and that something is e to the t. Next up, we have the Existence Uniqueness Theorem. This theorem states y prime plus p of t equals, y prime plus p of t times y equals g of t. Y to the t0 equals y to the 0, or equals y0. If p of t and g of t are both continuous on an open interval a is less than t is less than b, pertaining to the initial value problem is guaranteed to have a unique solution on a, b. And notice that it is not brackets. That means that they can be different at a and b. Now let's apply this existence uniqueness theorem to our original equations a, b, c, and d. You will notice that this does not apply to a and c because they are just not of the right form. So if we are going to apply the existence uniqueness theorem to b now, you would notice that in the equation we have a t squared y prime, but we need a 1 y prime. It cannot have anything in front of it, beside it, or anything. So if we solve that, to get rid of that, we will divide everything by t squared, leaving us with y prime plus 4t over t squared times y equals cosine of t divided by t squared. Now we will let things equal to p of t and g of t. P of t will be equal to 4 over t because the t's cancel out, or at least one of the t's cancel out in the denominator. And then g of t would be equal to cosine of t over t squared. And remember that g of t is what the original equation was equal to. You can say this is discontinuous at t equals 0, from negative infinity to 0, and 0 to infinity is where unique solutions exist in these intervals. But y of negative 1 equals 2. So we have to find the correct interval where y of negative 1 equals 2. And specifically, we're looking at that negative 1. So we can say that t of 0 equals negative 1 is at the interval negative infinity to 0. Next, we're going to solve equation D. Equation D states that t squared minus 4t times y prime plus ty equals e to the t in the interval y of 2 equals negative 1. So we didn't use the intervals when we were determining if they were nonlinear or homogeneous in the earlier part of this video, but now we are using these to find for the existence uniqueness theorem. So if we now simplify this, we would get y prime plus t divided by t squared minus 4t. And y is equal to e to the t divided by t squared minus 4t. So now we can say p of t is equal to t divided by t squared minus 4t, and g of t is equal to e to the t divided by t squared minus 4t. That gives us the equation t squared minus 4t. That's the equation we want to examine from these problems. So if we simplify that, we will get t times t minus 4 equals 0, giving us that t is equal to 0 and t is equal to 4. And that gives us the interval. 3 intervals: negative infinity to 0, 0 to 4, and 4 to infinity. So looking back at our given interval, y of 2 equals negative 1, we can conclude that t0 equals 2 at 0 to 4. And a reminder, that is where a unique solution is found. Moving on to our next example, we have for each of the initial conditions, determine the largest interval a is less than b, or a is less than t is less than b, on which theorem guarantees the existence of a unique solution. And we are given the problem y prime plus t divided by t squared plus 1 times y equals sine of t. It's important to note that this is non-homogeneous as well because it is equal to something. So p of t would be equal to t divided by t squared plus 1, and g of t equals sine of t. So the equation we want to examine is that t squared plus 1. and we will notice that there is no discontinuities in that. So a unique solution can be found anywhere in the interval negative infinity to infinity. Now for our next example, we have y prime plus t divided by t squared minus 4 times y. This problem will be homogeneous because it is equal to 0. So if we let p of t equal t divided by t squared minus 4, and we will let g of t equal 0, we will want to examine that t squared minus 4. So after examining that, we would get t equals negative 2 and 2 because of that square root, leaving us with the intervals negative infinity to negative 2, negative 2 to 2, and 2 to infinity. So if we were given an interval, we could find where a unique solution was found for that problem, but we were not given an interval. And finally, for our last example, I just want to state that you need to be careful to catch all of the discontinuities because they can be tricky to catch sometimes. In this problem, we have y prime plus ty equals tangent of t, given the interval y of negative 7 equals 4. So we're going to let p of t equal that t and g of t equal that tangent of t. So if you're looking for the discontinuities, make sure you're thinking about all of them. And for tangent of t, there are discontinuities at t equals pi over 2, and 3 pi over 2, and 5 pi over 2, and so on. 7 pi over 2, 9 pi over 2, and so on. So we are given these intervals from that negative 5 pi over 2, negative 3 pi over 2, negative 3 pi over 2, to negative pi over 2, and so on. These are our intervals. And if we approximate negative 5 pi divided by 2, we would be at about negative 7.8. So that means that from our initial given interval of y of negative 7 equals 4, we would find a unique solution at negative 5 pi over 2 to negative 3 pi over 2. That concludes this lesson. Thank you for watching.